Yeah, it's really a great pleasure to come here and to meet everybody and to share some of my latest learnings, actually. So this is also something I have been learning about and working on. And the thing I'm particularly going to talk about is this topic I wrote down, duality in the topological holography framework. Is a paper that's coming out, so we're still finishing it. So this is very new, but I thought since I'm so much excited about this topic, so I want to share what I learned with everybody and also get feedback and to get discussion, get a lot of questions, just not rotten eggs. Um, so this has been a very exciting field lately, and actually, it's very much related to some of the previous talks that you have already heard uh, at the summer school, including Xiaogang's talk, Caroline's talk, and Shuheng's talk. And there are several keywords floating around, including generalized symmetry, categorical symmetry, non-invertible symmetry, symmetry TFTs, so-called symmetry topological field theory, symmetry TO, the symmetry topological order, and topological holography. So there are lots of big words, very big words. So originally, I wrote the title as duality in the symmetry TFT framework. And I changed it not because I'm changing anything about the talk, but rather because I'm not sure which word to use. I think, so at least for my talk, I'm going to use these three words interchangeably. So one is topological holography, symmetry TFT, and then symmetry TO. I'm not going to when I say those words, I will not be referring to any difference between them. So I'll be referring to pretty much the same thing, although as Xiaogang mentioned, there might be some subtle difference between the concepts. But and I hope that maybe after my talk, I can also get discussion and feedback as a community. Maybe we can also think about what's the best way to call these things, because I feel like there's a overflow of terminology in the field right now. But that's a secondary issue. Okay. So I decided to talk about duality also because I think on the one hand, duality is a very interesting subject, but on the other hand, it's an opportunity for me to really go into details about some of the most illustrative examples within this symmetry TFT, symmetry TO topological holography framework. It gives me an excuse to talk about that. And I think that duality will also show the power of this framework. So for me, I think from my perspective of working on this subject for a while, the power of doing things in this framework is the separation between what we usually call the kinematic part of a system versus the dynamic part of a system, where the kinematic part may involve like degrees of freedom, dimension, or the symmetry, in particular the symmetry of a system, while the dynamical part involves all the Hamiltonian or Lagrangian you can write down, whether it's a gap phase or gapless phase or at a critical point. So by putting things into this framework, we can very nicely separate the two so that a lot of structure becomes more clear. Okay, so of course, here now they're very abstract notions, but hopefully after my lectures, I'll be able to demonstrate to you why this is the case, why this framework helps. Okay, so I have 3 lectures. I'll be, I think, the first lecture today, tomorrow, and Friday. And my plan is to be very, very specific and pedagogical. And as a more condensed matter person, I'm going to be mostly talking about very concrete lattice models. And I'll be talking about all of my favorite lattice models like toric code, Ising chain, and then generalizations from there. Okay, so I suppose these models have already shown up more than once. I think it will be helpful now to put it into this framework and see how things work out. All right, and any question is welcome. Don't hesitate to interrupt any point. Okay, so to introduce this subject, I'll generally call this symmetry. To introduce this framework of symmetry TFT, symmetry TO, or topological holography, I'll be talking about a food that is the sandwich structure that people talk a lot about. You might have heard about more than just sandwich. People talk about sandwich, people talk about quiche, people talk about tacos. So there are different versions. I'll be talking about the most, my favorite version, the sandwich version, and see how by thinking of the layer structure of a sandwich, we can separate what I call the kinetic part and the dynamic part of a system. And as I said, I'll be very concrete with a simple example. And in particular, I'm going to start from a 1 + 1D sandwich where and the meat in the middle is the 2 + 1D toric code topological order. And then we'll try to use that to study the 1 + 1D Ising chain. Okay. And since I'm going to talk about duality, you might have guessed that I'll try to talk about the Kramers-Wagner duality in the Ising chain and how that's realized in the sandwich structure. So I won't use very abstract words anymore. I'll just directly jump into this example, and hopefully, once I illustrate this example, it'll be clear what this framework is talking about. Okay. Okay, so so let's first review the 1 + 1D transverse field Ising model. This is, of course, everybody knows it and has shown up in their summer school. I'm just writing it down and talk about it again. So this is a spin 1/2 chain with transverse field and then with Ising coupling between nearest neighbors. Everybody knows this. So, so there are two phases. The system, first of all, has a symmetry, a global Z2 symmetry, which is a tensor product of the sigma x. And then there are two phases. When G is much, much smaller than 1, this is in the symmetric phase. When G is much, much bigger than 1, we're in the symmetry breaking phase. And then at G equal to 1, we're at the critical point. And famously, there's a Kramers-Wagner duality, which maps between the symmetric and symmetry breaking phase while keeping the critical point invariant. So our goal, of course, this is all very well understood, and Shuhong talked about it in terms of non-invertible symmetry and all that. So I'll be just doing that all over again, but do it in a more complicated way in this structure of a sandwich. Okay. So first, let me say how I want to realize this as a sandwich. Okay. And as promised, I'm going to make this more complicated. Instead of just having a one-dimensional chain of spin 1/2, I'm actually going to start from the 2 + 1D toric code, which is a 2 + 1D topological phase, topological state, and then add some structure to it in order to reduce it to this 1 + 1D system. Okay. So I'll draw a two-dimensional square lattice. Like this. And we're going to take a periodic boundary condition between the left and right. Okay. And the top and bottom are intentionally left open because we're going to do something about that. Okay. And this is just the regular 2 + 1D toric code with the Hamiltonian that everybody's familiar with. So the toric code has a Hamiltonian. One is the plaquette term, which we call BP, composed of 4x. And then there's a AV term composed of tensor product of 4z. Everybody's familiar with that. And the Hamiltonian, if this is just the bulk model, and then we have the sum over all BP and the sum over all AV. Okay. And if this is just the bulk model, and if we put it on, let's say, some closed manifold, we know that this model represents the topological order, and it will have some ground state degeneracy depending on the topology of the manifold. For example, if this is on a two-dimensional torus, there's going to be some loop operator winding around the torus. So one of these loop operator is the string of sigma x along a non-contractible loop. So I'm going to label this as W WEX, where the superscript of E indicate that this is the string operator that we use to generate the anion excitation E, the gauge charge excitation. And then there's another non-trivial string operator, which goes along the dual lattice of a bunch of Z. And this is what I call the WMX, meaning that this is the string operator for generating the gauge flux excitation. This is the same old story of toric code. Okay, so that's very nice, very well, all very familiar stories. But instead of just having toric code on a closed manifold, we're now going to play some tricks, both from the top and from the bottom of this state. We're eventually going to reduce it to a 1 + 1D strip. And what we're going to do to the top is that we're going to choose a particular gap boundary condition for the top boundary. Okay, so in the semi construction, it's a very specific requirement that the top boundary is fixed into some gap state. Okay. And famously, toric code has two types of gap boundary condition. One is what we call smooth, the other is what we call rough. So let's pick one. We're going to pick this smooth boundary condition for now. Okay, and then later we're going to talk about the rough one. And it's the name is a very good name because it literally means that we terminate the lattice in a smooth way so that there's no edges sticking out. This is the smooth termination of a boundary. And what that means for the Hamiltonian term is that on the boundary, we'll have three body ZZZ terms like this. So originally there are these four-body AV term in the book, but on the boundary, since there are no edges sticking out, this becomes a three-body Hamiltonian terms. And that's the smooth boundary. While the plaquette term is still four-body term because the plaquette is a full plaquette. Nothing is truncated about the plaquettes. The plaquette is still four-body. Okay, so we can check that everything commutes, and with this choice of Hamiltonian, the top boundary is completely gapped out. So this is one of the gap boundary condition of the toric code. And the physics interpretation of this boundary is that something condenses, okay? And in particular, we can see that if we draw a vertical WM string like this, so we have Z, 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 given by a WM Y operator, meaning that a string operator of Z in the Y direction. And this string operator actually commute with all terms, both in the bulk and also on the top boundary. We haven't specified what happens down here. We don't care what happens down here. But at least in the bulk and on the top boundary, everything commutes with this string operator. So this WMY string, even though in the bulk, if it terminates, it's going to create an excitation, we see that on the boundary, if it terminates, it's not creating an excitation. So in that sense, we say that this smooth boundary is where the M flux excitation condenses. Smooth boundary. Excuse me, is there a question? Oh.
Boundary term on
it. It commutes with plaquette terms like this because they intersect twice, and it commutes with the ZZZ term because they're all Z's. I think, excuse me?
Oh, sorry.
Yeah, yeah, it's good to check my algebra because I make algebra mistakes all the time. So the smooth boundary is where the M excitation condenses. Right, and this is actually a general rule for having a gap boundary. I think this is also what Caroline mentioned in her talk, that if we want to have a gap boundary of a topological order, we better have something condensed on the boundary. I need to have sufficient amount of things to condense on the boundary. And for the toric code, it turns out we just need one of the bosonic anyons to condense. So it's either M or the E particle. And with the smooth boundary, it's the M condensation. And with the rough boundary, it's going to be the E condensation. Yes?
The gap boundary. What does gap mean?
Right, what does gap mean? It means that so I haven't specified what happens down here. But in the simplest case, let's say we have a disk of toric code, and it's smooth all around on the boundary. And you can exactly solve for this Hamiltonian and see that it's gapped. There's a unique ground state, and no gapless excitation along the boundary. Yeah. So in that sense, then here, even though we haven't specified what happens on the lower boundary, you can show that there will be no gapless excitation on the top boundary. If there's anything, there's going to be on the lower boundary. Okay. Good. Okay, so this is the bulk and the top boundary. So for anyone who's familiar with the story of toric code, this is very old and very well known, and this is nothing new. Okay. And in the sandwich story, what this bulk term and the top boundary term does is to specify what we call the low energy Hilbert space. Okay. So the sandwich structure will effectively reproduce the low energy sector of the 1+1D transverse field Ising model. And the low energy sector is given by specifying the bulk Hamiltonian term and the boundary Hamiltonian term and fix them to be in the ground state. So we force all these terms to have eigenvalue 1. Okay. And we don't allow any excitations because, as I said, all the dynamics will be separated and all the dynamics will be on the bottom boundary. Okay. All right. And this is, of course, possible because all the terms commute. So we force all the terms so far, and the bulk Hamiltonian and the top boundary Hamiltonian to be in eigenvalue 1. Okay. Okay. So before I talk about what happens on the lower boundary, first let me talk about these string operators running through the bulk. Because I just said that I want all the bulk term and all the top boundary term to have eigenvalue 1, but that still leaves me some freedom with choosing the eigenvalue of the string operator, because these string operators, they commute with all the bulk terms and all the boundary terms. So these are some leftover degrees of freedom. And turns out these will become potentially defining the symmetry of the sandwich. So let's look at what can happen for this Z string operator, this WMX, and also the X string operator of WEX. Okay. So first, let's look at the Z string operator. The Z string operator, it commutes with all the Hamiltonian terms I've specified so far. But actually, if you look carefully, it's not totally free, because this Z string operator is a product of all these three-body boundary terms that I've put on the top boundary. Right? If we multiply all these three-body terms, and this is periodic boundary condition, remember, periodic boundary condition from the left to the right, they actually multiply into this Z string operator. So that means that once I choose this top boundary to be smooth and force that there are no excitations on the top boundary, then actually this WMX has to be equal to 1. So this is already fixed. This is not something that I have freedom with. Okay? So meaning that once I choose this boundary, this is already a fixed number. And later we're going to see that this actually labels the so-called flux sector of the 1 + 1D Ising chain. Okay, but for now, we see that this is fixed. This is just a number. Okay. On the other hand, if we look at the X string running through the bulk, this string is not fixed by the top boundary. It's not part of the so-called stabilizer group. Right. Even by specifying all the bulk and top boundary terms, I have no information about what this WXE should be. And this is, of course, a Z2 operator, so this WXE can take value of ±1. Okay. So this actually becomes the Z2 symmetry of the sandwich, because it commutes with everything. And then the nice thing is that because this operator is actually a bulk operator, so it floats in the bulk. So whatever term I write on the bottom boundary is going to commute with it, right? Because they're spatially separated. So as long as I write Hamiltonian terms, dynamic terms, only on the lower boundary, all these terms will be automatically Z2 symmetric. So this is the power of this sandwich structure. It separates the symmetry away from the dynamics. And then we also see that this symmetry becomes a rather topological symmetry because you can wiggle the string through the bulk and change its shape and change its exact location. It doesn't matter. It's still the Z2 symmetry operator of the sandwich. Yes?
Why don't you give the WEX operator exactly at the smooth boundary?
Why don't I choose the WEX operator exactly at the smooth boundary? I can. They're all equivalent because I can use all the plaquette terms to move the location of the string. Yeah. So it doesn't matter where I put it.
What is the operator that ends at the perpendicular operator that
Oh,
ends
yeah.
at the boundary play the role.
Yeah, the perpendicular operator is something I'm going to talk about right now. Yeah. So, so this WXE operator, as I just said, it can take eigenvalue plus minus 1. It's going to become the Z2 symmetry operator of the sandwich. And then because this WYM operator anti-commute with this horizontal X string, right? So that means that this WYM operator is actually the Z2 charge operator of the sandwich. So in the Ising chain, it would actually correspond to a single sigma Z. Okay, although here it has some extension. It's the cost of having a sandwich structure. The charged operator need to traverse the whole thickness of the sandwich and tunnel from the bottom to the top. W, Y, M, anti-commute with the symmetry. Okay. Okay. Is there any way I can? Oh, here. Is this how it's done? Oh, okay. Okay. I see. Okay, then let me just not use that. Actually, yeah, let me erase the title. The title doesn't contain too much information. Actually, I need to draw on that graph. Sorry. Oh, can I bring it down? Okay, I can. Sorry. Okay, I still want to draw on this diagram, but let me use a sideboard to write. Okay, so now I want to talk about the bottom boundary. The bottom boundary is left open, and a bunch of things can happen. And what can happen? There's not much rule for what can happen. The only thing that we need to be careful with is that we need to make sure whatever happens on the bottom boundary doesn't mess up with the bulk and the top boundary, right? Because that's the low energy Hilbert space we have specified. We don't want to get out of it. So whatever happens on the bottom boundary, we want it to commute with the Hamiltonian terms in the bulk and Hamiltonian terms on the top boundary. We don't need to worry about the top boundary because it's very far away. We just need to put some terms that commute with all the bulk terms of the toric code. Okay, so there are two types of local terms that we can add on the bottom boundary. There's so many colors, so nice. Okay, one type of term is this three-body ZZZ term. It's actually the same as the one we use to define the top boundary, and you can check that it still commutes with the bulk. So it's a kind of term we can put on the bottom boundary. Okay. And another type of term we can put is a single X, like this. And you can also check that it commutes with Hamiltonian terms in the bulk, and we can safely add it to the bottom boundary. Okay. So the difference from the top boundary is, for the top boundary, we only pick one of the terms to define the top boundary, because we want the top boundary to be fixed, to be gapped, and of course, we pick a specific exactly solvable point of the top boundary. But on the bottom boundary, we can have both. And this ZZZ term and this X term, they don't commute, right? They will have some non-trivial competition among themselves. And once we add them with different weight, we're actually going to be in two different phases and even drive a phase transition. So that's how we mimic the dynamics of the 1+1D transverse field Ising model. Okay.
Is the Fouquet term still there?
Excuse me?
Is the Fouquet term still there?
Right, so there's a question of where do you terminate the bulk? So we terminate the bulk term at somewhere. So for example, we have this ZZZZ term, but we don't include the Fouquet. We have to terminate at some point. I can't let it go on forever. So this is a rather free choice where you exactly terminate the bulk. But once we choose, we set a location where the bulk term cease to exist, then we're free to put any term that can be used. Yeah, so I'm saying that maybe we don't include this full body Fouquet term. Or actually we do, we can. But we don't include like terms down below. So we terminate the bulk at some point. Yeah. Right. So in order to see how the correspondence work, how this more sophisticated sandwich structure reproduce the 1+1D transverse field Ising model, we need to match these terms with the Hamiltonian terms of the Ising model. Right? And we should be able to do that because we see that this sandwich has a Z2 symmetry, and the Z2 symmetry is something that floats in the bulk and doesn't even touch the bottom boundary. And now we're writing some boundary term that obviously commute with the bulk symmetry, so they should represent some symmetric Hamiltonian, local Hamiltonian terms that we should be able to match with these operators. Okay, and the trick is, how do we match them? So one clue is that we already know what is the symmetry charge operator. This is the symmetry charge, remember? Because this is the operator that anti-commute with the Z2 symmetry. So this is actually going to be the symmetry charge. And it's of course important that this is not an operator that's confined to the lower boundary, because otherwise it will commute with the symmetry. And it's a string operator that extends to the top, so it can potentially carry a symmetry charge. Okay? And from here, we'll be able to guess what these two operators represent. Okay, so let's look at this ZZZ operator. This ZZZ operator, of course, it's localized on the boundary, but if we look carefully, we can see that this is equivalent to the product of two such vertical string operators up to bulk and top boundary terms. Okay. So if we have a WYM here and a WYM here on these two vertical lines, and we multiply them together, and then we can multiply a bunch of top boundary term and bulk terms because they come for free, they're set to be 1. And once we multiply all of that, we'll see that this is equivalent to the three-body ZZZ term on the lower boundary. Okay, so this is telling us that, let me just write it here, that this ZZZ term becomes equivalent to the Ising coupling term, the sigma Z term. Okay. And then from there, it's easy to guess what this single X would be, because a single X would anti-commute with the neighboring ZZZ term, right? So from the analogy of the Ising chain, we can very easily guess that the single X becomes equivalent with a single sigma X. And we can check that the product of a whole string of this X operator reproduce the Z2 symmetry operator up to bulk terms. So this is the how the operators correspond between the two sides. Yes.
How do you get the Z on the middle? Sorry, on the bond from multiplying the WYs?
I mean specific. So I take a string operator on this line, the WMY, and I take another one, WMY, on this line. Let me just draw it here. It's getting messy. The picture is getting too messy. Okay, so I have string here and a string here. So I have Z, 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 and Z, 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 Z. Okay. So I multiply these two together, and then I multiply a bunch of stabilizers, the boundary term and bulk term. So the boundary term is this one, and then I have full-body bulk term, bulk term, bulk term, bulk term. If I multiply these two strings together with all the circles I've drawn, you will see that it reduces to a three-body ZZZ term. Yeah, it works. Okay, good. Yeah, so let me just briefly recap. We have a bunch of different things going on in this diagram, right? So a lot of colors. First of all, there's the Hamiltonian terms in the bulk and on the top boundary. The Hamiltonian terms in the bulk and top boundary, they're fixed. They're fixed to take eigenvalue 1, they're in the ground state, and they define the low energy effective Hilbert space of this sandwich. Okay, so that's the first thing. And usually we don't want to violate them. They're set to be 1. Okay? And on top of that, we have the horizontal string operator that commute with all the bulk terms and boundary term and the top boundary terms, which means that these horizontal string operators, in principle, they can act in the low energy Hilbert space. But some of them might act in a trivial way. Some of them might already be fixed by the top boundary. So they're kind of boring. While others can act in a non-trivial way, giving rise to a non-trivial symmetry. And once we determine which one gives us the symmetry, we can identify the symmetry charge operator, which usually is a string operator that tunnels in the vertical direction. In this case, this is the WMY operator. Okay. And after that, we look at Hamiltonian terms on the bottom boundary that commute with the bulk term and commute with the top boundary term. And those operators will be the symmetric Hamiltonian terms that we can write down for the sandwich because they're spatially separated from the location of the symmetry. So they definitely should be symmetric. And the interpretation of these operator in terms of the original spin 1/2 chain, we can find out about that by comparing that with the action of a single charge operator. Right? So we know the single charge, and then we see which one is the Ising coupling and which one is the transverse field. And that tells us what effective model we have once we specify some dynamics on the bottom boundary by writing down a Hamiltonian for the bottom boundary. Okay, so let me just summarize things here because later we'll compare to the other case. Because this case is a smooth boundary. With a smooth boundary, we have WEX is the global symmetry, which is the product of sigma x, and WMY is a single charge operator, while the ZZZ term on the bottom boundary is the Ising coupling term, while the single X on the bottom boundary gives us the transverse field. Okay, so I'm going to keep this one here because later I'm going to compare this to the version with a rough boundary. where we see that the interpretation is swapped. It's the other way around. Yes.
Why don't you write the bottom X in the sum operator?
I don't have to. And so yeah, so it's not the Ising term. So yeah, it's not a composite of charge operators. Yeah, so basically, there's always some ambiguity in explicitly identifying which operator is which, but as long as the operator algebra is the same, then it will give rise to the same dynamics. Okay. Okay. Oh, yes. Yes. Once we, sorry, I forgot to mention that. So we started from a 2 plus 1D Charcot, which is a 2 plus 1D system. But in order to reduce it to this 1 plus 1D transverse to an Ising model, we'll take a sandwich that's of finite height in the Z direction. Yeah, so then it effectively reduces to a 1 plus 1D model, although it's a model with meat in the middle. So it's only a finite separation in the y direction. Yeah, thank you. That's a very important point.
Is it stable against perturbations in the ball?
Yeah, the bulk is gapped, so everything's stable. Yeah.
But okay, I see. So in that case, you just have Ym and still at the charge operator, even though they will be dressed.
Right. Once we compress the sandwich to be of finite height, it will be a local operator. It will be a local charged operator. So if you're allowed to break the symmetry, you can add it. But if you're not allowed to break symmetry, you cannot add it. It's the same story as Ising model. Right. Okay. Okay. So before I move on to talk about the Kremer-Vanier's duality, I actually want to talk a bit more about this operator, this boring operator that we set to be 1. Because I'm going to actually be talking about a slightly more complicated version of Kremer-Vanier than what Shuheng has been talking about. So when Shuheng was talking about this non-invertible symmetry, the Kremer-Vanier dualities projects into only the symmetric subspace. And the power of this whole sandwich construction is that we can actually very easily also include the charge sector and the flux sector. So all 4 sectors in this case. So this is a Z2 global symmetry. We're going to have charge and flux both being a Z2 label of the symmetry sector. So we're actually going to have 4 sectors in total. And we're going to see that the Kremer-Vanier duality is a mapping among the 4 sectors. Okay, so it keeps the no charge, no flux sector as itself. So that's a very nice mapping to itself. But then they will permute between the charge flux sectors. So I want to talk about how the flux sector is realized in the sandwich picture before I talk about the duality. Okay, and the flux sector will have to do with this boring operator, which takes eigenvalue 1 because it's set by the top boundary already. But we want to make it not 1. And how do we make it not 1? It's by picking one of the top boundary term and set it to be, just set it to be -1. So we have a kind of have a defect at the top boundary. We just pick a location and set that point to be -1. And once we set one of the boundary term to be -1 so that we have a defect on the top boundary, this string operator, this W mx can also take value -1. Okay, but it's slightly different from the choice of WXE being ±1 because we see that now we need to introduce a defect on the top boundary. So that's actually an indication which one is flux, which one is charge, because in the original 1 + 1D Ising model, this Hilbert space contains the no charge sector and the charge sector. It actually doesn't contain the flux sector. The flux sector is something different. And in this picture, we see that once we fix the top boundary, we can have no charge sector and the charge sector. But if we want to have the flux sector, we need to do something slightly more dramatic. We need to have a defect on the top boundary. But other than that, we see that the flux sector and the charge sector actually has a very large similarity between them. They're just labeled by the ±1 eigenvalue of the horizontal string operator. Okay, and this is going to play a very important role later in our discussion when we talk about dualities, because just a spoiler alert, duality in the sandwich structure will only correspond to a change of the top boundary. It doesn't touch the bottom boundary. It doesn't even touch the bulk. Okay. So these string operator in the bulk, they're left invariant. We don't even touch them. They are what they are. And since these kind of things label the symmetry sectors, that's how we can match the symmetry sector before and after the duality transformation. So this will all become more clear once I do talk about duality, but this is just saying that why this symmetry sector labeling being in the bulk is an important feature that we should keep watching for. There's a question.
So doesn't introducing the top defect also screw up the one in the items on the bottom, because like in the picture you drew where you applied by like the stabilizers?
Exactly. Yeah. That's a great observation. That's exactly the feature we should have. Okay, so that's actually I want to talk about. So how do we see? I haven't explained why setting this to -1 and setting this term to be -1 correspond to the flux sector of the transverse field Ising model, and that's exactly why. Because in the transverse field Ising model, let me just do it here. Let me put a plus sign to this Hamiltonian, meaning that everything's translation invariant. This is what we call periodic boundary condition. Right? And once we introduce a flux, usually what we do is to take the boundary term, take the boundary Ising coupling term, and add a minus sign to it. So the H minus Hamiltonian is sum over transverse field. The transverse field part doesn't change, but the Ising coupling part, most of the terms don't change, but the boundary term will have a minus sign. So this is what we mean when we say we'll add a flux to the Ising chain. Okay. So you see that in the transverse field Ising model and in all of these models we consider, the flux sector is by changing the Hamiltonian to something different. Right? The flux sector is obtained by modifying the Hamiltonian along a defect line. So why do I claim that by setting this string operator to be -1, we actually recover this Hamiltonian? This is because now if this term is -1, and then we use this equivalence to map the bottom ZZZ term to an Ising coupling term, this term is going to come with an extra -1. Right? So yeah, exactly your observation. So So actually what we do is that we don't touch, when we try to, in the sandwich picture, when we try to get to the flux sector, we're not changing the Hamiltonian. We're not adding a sign to this ZZZ itself, but rather we're looking at the sector where the horizontal string have different eigenvalue. Okay. And this is very important because when the horizontal string have different eigenvalue plus minus 1, these sectors, they are in orthogonal Hilbert space. Okay, so the charge sector and the flux sector are in orthogonal Hilbert space. This is a very important feature, but it's not obvious in the original 1 plus 1D version of the story, because in the 1 plus 1D story, it looks like they live in the same Hilbert space. They live in the same one-dimensional chain of spin 1/2, n of them, but rather the Hamiltonian looks different. Okay. But the sandwich construction makes it very clear that the charge sector and the flux sector are orthogonal sectors. Okay. And that will become important once we consider like partition function of the Ising CFT, because we'll be able to talk about how we add the partition function from different sectors. Right, so it's a very important notion that that effectively we should think of all these sectors as orthogonal Hilbert space. Right. And then we see that the way we actually get to the flux sector is not by changing any Hamiltonian term, but rather restrict to the sector with a -1 horizontal string operator. Okay, everyone getting confused? Oh. Fine. Okay, right. Yeah. So this is I like the sandwich structure just because it makes the symmetry sector structure very clear. Okay. Of course, one thing we sacrifice once we go from this construction to this construction is that here we don't have a tensor product Hilbert space anymore. Here we only have an effective low energy Hilbert space specified by the bulk Hamiltonian terms and the top boundary Hamiltonian terms. It's the Hilbert space is not a tensor product anymore, although we can recover the correspondence of the symmetric operators on the lower boundary. Okay, and if we do want to keep the tensor product Hilbert space, what we sacrifice is that the flux sector looks very weird. It looks like something with a different Hamiltonian, but living the same Hilbert space. Okay. Okay. All right. So this is all the feature of the sandwich construction I want to talk about for this particular example of 1 plus 1D transverse field Ising on the boundary of 2 plus 1D toric code. And you might see why they're associated with big words like that, like topological holography, because this is realizing something on the boundary of a higher dimensional topological state. And it is about separating the symmetry into a more topological operator into the bulk of the topological state. So that's maybe why it's called symmetry TFT and symmetry TO. But for me, more or less, I think of this sandwich picture when I read those words. Of course, in the literature, there might be subtle differences, but to zeroth order, this is what I think about. Okay. So just let me try to summarize the general structure of this topological holography or the sandwich picture. What happens is that, I'll write it over there. So a sandwich has a structure that the bulk is a d plus 1 dimensional topological order. So here we have an example where the bulk is 2 plus 1 dimension, but we can go to higher dimension. And the higher dimension version will be the more interesting and more open questions. The 2 plus 1D version is, the bulk is more understood, and the boundary is more understood as well, because the bulk is 2 plus 1D topological order specified by its anyons of braiding and fusion and all the data Caroline was talking about. And also the boundary, it's a 1 plus 1D, usually CFT, so there's also a nice analytical understanding of that. But going to even higher dimension is a very exciting direction. And then the top boundary will be gapped. And as Caroline talked about, the way to gap out the boundary of a topological order, we need to condense something, right? So if it's 2 plus 1D topological order, we condense some anyons. If it's even higher dimensional, we need to condense more complicated objects, and I don't even know if that's fully understood. There's some big words associated, like higher fusion category. Yeah, but there's a lot of open question there. And then the bulk and top boundary term define the low energy effective Hilbert space, and the bottom boundary contains all the dynamics. This is just the general structure. And then horizontal logical operators parallel to the boundary in the bulk define the symmetry sectors. So if we go to higher dimension, these operators won't be just string anymore. Like if the bulk is 3 plus 1D, and then we can also have membrane operator that's parallel to the boundary, such that the lower boundary terms all commute with it. And those membrane operators will also be part of the labeling for the symmetry sectors. And then the vertical string operators, they can commute. They will have non-trivial commutation with these labelings, so they can toggle between either the charge sector or the flux sector. And the choice of which horizontal logical operator labels charge, which one labels flux, is determined by the top boundary condition that we choose. Okay, so this hopefully is all clear from that example that I showed. Of course, in other cases, things can be more complicated, but the general principle is the same. Okay. Yes.
And the perfectly flattened model, we now make a connection between the algebras between the operators, but I don't still see how G is coming in 2 plus 1.
Oh, the G is because when I write these operators, they can come with weight.
So like when G is 1, it is exactly CFT.
These two terms are added with same weight. So the bulk term, they all commute, and they're set to be, let's say, infinity, weight infinity, and they have to be in the ground state. But the boundary term, these terms, they don't commute. So when I add different weight between them, the system will be in different phases.
Boundary also be gapless when G is 1.
Yeah, yeah, exactly. So you tune to the critical point by setting the weight of these two terms to be the same, and then add all over the bottom boundary. Yes.
Does the way we truncate on the bottom boundary make any difference?
Nothing important. So it might look slightly different. Like you might return more degrees of freedom or something. The term might get bigger, but eventually it won't matter. Yeah. Okay, so let me give a few more examples of what this sandwich might represent if we choose different bulk and then different top boundaries. So over there, we did the simplest case where the bulk is 2 plus 1D toric code, Z2 topological order, and with one of the boson being condensed, and the sandwich reduces to a 1 plus 1D spin chain with global Z2 symmetry. And it's a very ordinary kind of Z2 symmetry with zero form and no anomaly, right? But if we choose some different kind of bulk topological order, we can get more interesting cases. For example, if the bulk is 2 plus 1D double semyon. If the bulk is 2 plus 1D double semyon, it's a legitimate 2 plus 1D topological order. And we know that there's only one type of boson within this topological order. So that's the only way we can get a gap boundary. So double semyon, and we'll condense basically the Z2 gauge charge on the top boundary. Condense. And then what happens is that the string operator of E, this is set to be 1 by the top boundary unless there's a defect and it becomes -1. But then the other one, the semyon string operator, being a Z2 operator, this one can have eigenvalue plus minus 1. So the semyon string operator becomes the Z2 symmetry of the sandwich. So the sandwich, once we compress it down, it becomes a 1 plus 1D system, a 1 plus 1D spin system with zero form Z2 symmetry. But this zero form Z2 symmetry is anomalous. The way to see that it's anomalous actually is by realizing that the only way we can make the bottom boundary gapped is again by condensing the E particle. Otherwise, it will be gapless. But the only way to make the bottom boundary gapped is to also condense the E particle. But once we condense both the top boundary and the bottom boundary with the E particle, we can tunnel the E particle. We can tunnel the E particle between the top and bottom boundary without creating any excitations. Okay? And once we tunnel the E particle in the vertical direction, we're actually going to change the eigenvalue of the symmetry operator because the semyon and the boson, they anti-commute with each other. They have braiding statistics -1. Right? So that means this vertical green line is the symmetry charge. It's the Z2 symmetry charge. So if we have a state and we can add a Z2 symmetry charge without creating any excitation, that means we're in the symmetry breaking phase. Right? If you have a GHZ state, you can add a charge without costing any energy. But that's the only way to gap the system out, meaning that the symmetry has some anomaly because there's no way to gap it out without breaking symmetry. So that's kind of almost a definition of anomaly. Right. So with double semyon, we get a 1 plus 1D spin chain with Z2 symmetry, but anomalous Z2 symmetry. And then the second example is the 2 plus 1D doubled Ising. This is a non-abelian topological order where in the bulk we have some sigma particle and we have some psi particle. Okay. And we choose the doubled Ising so that, again, there can be a gap boundary at the top. Okay, so if we choose the chiral version, of course, the boundary will be chiral. But we choose the doubled version of the topological order, then the top boundary can be gapped out. And there's actually only one way to gap out the top boundary of the double Ising is by condensing all the doubled anyons. So it's condensing both psi bar and sigma bar. If you're familiar with the notation of anyons in the double Ising, and there are two copies of anyons. One is 1 psi sigma, the other is 1 psi bar sigma bar. And when we multiply them together, we get 9 anyons. And the double ones are bosons, and we can condense them on the top boundary to get a gap boundary. Okay? Yes?
Can you
leads to gap boundary in general?
Right, so we need to use what Caroline was talking about, that once you condense all these, nothing is left over, everything's either confined or condensed then. Yeah.
Can we have parallel topological order in the bound?
Right, if we have pure topological order in the bulk, we won't be able to gap out the top boundary. So that's not within the framework I talk about. Okay, so once we condense psi bar and sigma bar, then following all the arguments we had before, we see that the string operator of psi bar x and sigma bar x becomes the boring operators, while the other ones, like psi, a single psi, and the single sigma, becomes the more interesting ones, becomes the ones that can actually act non-trivially within the low energy Hilbert space, right? So these blue ones, they actually give us non-trivial symmetry transformations of the sandwich. But due to the non-abelian fusion rule of the sigma particle, we see that this actually gives us a non-invertible symmetry, exactly like what Shuheng was talking about. So this the symmetry actually satisfy the fusion rule of sigma and sigma fusing to 1 plus psi. Well, psi is a Z2 symmetry, it's a normal Z2 symmetry, but sigma is a non-invertible symmetry. And this is a way to realize the Kramer-Vanier as a non-invertible symmetry with the sandwich. Okay, so these are two examples in 2 plus 1D. And then the last example is a 3 plus 1D example, which I'm actually going to talk more in my later lectures if I have time, but I'm going to briefly mention it today. So let's say if the bulk is 3 plus 1D toric code. Yes.
Double Ising case, as you collapse the sandwich, is the resulting 1 plus 1D lattice model, does it have a tensor product Hilbert space?
In general, these things don't have tensor product Hilbert space. Yeah. Yeah, so that one.
Well, probably not, right? You realize Ising fusion category on the spot.
Yeah. Exactly. I think in general, it's hard to, I don't know how to say whether there's, or whether there's literally a way to map it back to a tensor product Hilbert space structure, given the sandwich. Actually. If there's no anomaly or none of these non-invertible things, then I'm more confident about it. Right, so with a 3 plus 1D bulk, the sandwich will look like this. Yes.
Follow up on this question. So if I did the whole thing in the continuum, I wouldn't see a difference between the case where you have a tensor product Hilbert space or not. I'm just doing something else. So how will I tell the difference in the continuum?
The difference between
these two cases where you do not get. So when you collapse the sandwich, you say that sometimes you end up with a tensor product Hilbert space, sometimes you do.
Right, all I can say is that sometimes it does correspond to a model with a tensor product Hilbert space, but I don't know how to go from a sandwich structure to rediscover the tensor product Hilbert space. I only know that because in this case, I know it's originally this one. But if you just give me a sandwich, I actually don't know how to recover.
Distinction between the two cases, or is it just that you don't know?
Maybe just, I don't know. I'm not sure. So if the symmetry is non-anomalous and then invertible, everything's a group, then I think it's probably true that there's a tensor product Hilbert space structure, but yeah, I don't know. Okay, so 3+1D toric code. So we can, this is also a well-known topological order, and it's a Z2 gauge theory in the bulk with bosonic charges and flux loop. And it's there's a lot of study about the boundary as well. And there are multiple ways to gap out the top boundary. And most famously, there's also the rough and smooth boundary, where the rough boundary corresponds to the gauge charge condense. And the smooth boundary corresponds to the gauge flux condense. Is it time already? I didn't ask for the warning, so I need to watch out for time myself. Yeah, so, and I'm actually going to continue tomorrow and tell you how these two type of boundaries, one correspond to, eventually will lead to a zero form Z2 symmetry once we reduce the sandwich to a 2+1D system, and the other one reduces to a one form Z2 symmetry. Okay, so to be continued.